time and we finish in time. So good morning, good afternoon, good night, everyone. Welcome to today's industry tutorial on high-power deformable mirrors for lasers and defense applications. My name is Elena Diaz, and I am the Director of Laser and Medical Technologies in Optica. And with me is John Pook, the Quantum and PHELIX Director, Technologies. I'll be your host, and we will be your host, and we moderate this exciting session. We are thrilled to see such a strong turnout with over 500 attendees from different sectors across the globe. This underscores the importance and growing interest in adaptive optics and technology for both lasers and defense applications. First, there is a big thank you to our sponsor and corporate member, Alpao, now part of the Bertin Technologies, whose innovations and support make this event possible. Appao is a leader in adaptive technologies optics, known for developing solutions that enhance the performance of high-power lasers across various applications. Their expertise is helping to shape the future for both defense and energy systems. We are fortunate to have two outstanding experts with us today, bringing unique perspective on cutting-edge applications of deformable mirrors. We start with Vivien, following by Jonas. After their presentations, we have time for a robust Q&A session, so please submit your questions in the chat box during the talks. We will be keeping an eye on them to ensure we address as many as possible. So let's start with our first speaker. So Vivien from Bertin Technologies brings hands-on expertise with lasers in defense applications, navigating the technical constraints and operational challenge for demanding field. He will discuss how adaptive optics can revolutionize the laser-based systems. Vivien is an accomplished expert in advanced optronic systems and their applications in defense and security. Now, he's currently the head of major defense accounts at Bertin Technologies, based in Aix-en-Provence region of France. Beautiful, beautiful area. So, Vivien, the floor and the attention is yours.
Thank you very much. Do you hear me? Okay, perfect. So hello everyone. Thank you very much for the kind introduction. I am going to share my slides. Do you see them? Okay, I guess so. So thank you very much for the kind introduction. Everything has been almost said, except maybe that I am very happy to be here at this webinar to talk about optronics and more especially the contribution of high-power deformable mirrors in our systems. So the main objective of my talk is to illustrate how high-power deformable mirrors can contribute to laser and defense application. And my talk is structured around the main following topics: a brief introduction to our company, Bertin Technologies, and our key positioning in optronics. I will do a presentation on a typical optronic system that we deliver, where adaptive optics and high-power deformable mirrors have added value. I will then introduce briefly the technology of adaptive optics, and finally, I will discuss on its contributions with a presentation on two concrete new applications for which high-power deformable mirrors are keys. So Bertin Technologies, who we are an European industrial group specializing in high-end instrumentation for critical or scientific application. We supply our customers with measurement and observation components, equipments, systems for critical application or scientific purposes. Critical application, and I will come back later on the talk, encompasses three key aspects. First, performance. Our equipments are highly performant, given the mission they are integrated into and the stakes involved. Robustness. Our equipments are designed to withstand demanding environments, shocks, vibration, temperature, so forth. And for example, we have optical components on Mars that they are embedded on the two rovers, Perseverance and Curiosity, and also on the James Webb Telescope. And the third key aspect is sovereignty. The critical components of our solutions are sourced from French and European supply chains. I will come back in my talk later on the two first pillars, performances and robustness, as they are of importance regarding the potential contribution of high-power deformable mirrors in our system. So some key figures, we are 700 employees, and we achieved a turnover of 132 million in 2023. Bertin Technologies comprises three main business units: Bertin Instruments, Bertin Wheellight, and Bertin Health and Life Sciences. And as you can see on the world map on the slide, we are based in France, mainly in the region of Paris and southern of France, where I am located, at Aix-en-Provence precisely, and across Europe with operational subsidiaries in Germany, Italy, United Kingdom, Sweden, and Finland. And we also have commercial offices in US, Singapore, and in the Middle East. Thanks to our key positioning on European presence, we contribute to industrial sustainability and European sovereignty with value proposition addressing the major challenges of our world. So we deliver solutions that contribute to security of people and nation. And as an example, we were part of the securization of the Olympic Games in Paris by contributing to the protection of key infrastructures, including the Stade de France. Our equipments are used for environmental protection and monitoring. And for example, we have air samplers, so equipment for air quality monitoring in hospitals to detect bacteria, viruses, pollens, and more generally pathogens. In the domain of decarbonized energy production security, we deliver health physics instruments to protect workers. So it's instruments dedicated to the detection and monitoring of radiation. And we are also highly involved in scientific knowledge improvement. I have already mentioned our contribution to space exploration, Mars, James Webb Telescope. We also have components on the JUICE probe, which is on its way to Jupiter. Another example is that we are involved in ITER, the fusion energy program, with equipments inside and beside the tokamak of ITER. So now, more precisely on the Bertin Wheellight, which is a business unit delivering high-performance optical and optronic components and systems for space, big science, surveillance, and protection. And our value proposition is built on high-performance optical system, and we have a unique expertise in this field on the dedicated production site in southern of France. Components for Mars, I have talked about, were manufactured here. Low swap, size, weight, and power on smart camera modules, infrared and visible with real-time embedded processes, including artificial intelligence, by the way. And we deliver very compact and efficient cameras for integration. And in a punchline mode, I usually say that we bring the image, not the constraint. We also provide our customers with ruggedized optronics modules and systems, mainly for vehicles and vessels, for 360-degree observation and surveillance in operation. And last but not least, complex optical instrumentation system. We respond to specific client needs based on their specific requirements. And the example shown here is our contribution to the ESA's LISA mission, the very large interferometer to detect gravitational waves, and based on a set of satellites that will be launched in 2035. And we provided this complex optical system called beam simulator for the LISA's ground equipment. I now present an operational system we delivered for a French integrator to support my presentation on how adaptive optics is an asset and how it can contribute to our systems. So we designed and delivered the optronic observation system, an optronic site, integrated on a new battlefield light vehicle for the French forces. So this is the picture that you can see on the right of the slide. It's a full imaging system for long-range identification with the main following characteristics. It has 4 viewing modes and a laser rangefinder. So yes, it's a complex and dense optronic system. It is adapted, as you can imagine, for this kind of application to harsh operational conditions, as it is integrated on the vehicle and operated on the field. It is integrated on a gyro-stabilized pan tilt unit. And the overall solution, the overall imaging solution, is based on a cost-effective uncooled imaging technology. It has to be noted that the notions of harsh environments, fine stabilization, and cost are constant in many of our projects, requiring above all high analytical performances. It's an invariant. And to, if I can say that, secure this combination of contradictory expectation and or extend the field of application for such a system, this invariance justifies the use of high-power deformable mirrors to push the limit of current technology and explore new fields of application. This is typically the case for this system, in which the introduction of high-power deformable mirrors opens door for optimization and new application. And this is what we are going to discuss now. So what's the point of high-power deformable mirrors? So to illustrate the importance of this technology, here is an ideal image if we imagine an object in a vacuum. So from the source, we emit a laser beam in red, and it works, intending to deposit energy on the object of interest, potentially very far away, as we are going to see in the application we are going to discuss afterwards, from a few kilometers to hundreds of kilometers, depending on the application. And in an ideal system without defects, the laser beam stays focused on the object of interest, and in return, its image remains focused from the source to the object of interest, and the energy re-emitted allows us to image the object of interest. Once again, in an ideal system, the return image is clear. We send a point, we bring back a point. But we are facing not an ideal world, but the real world. And in the real life, there are defects and disturbances that degrade performances by affecting the beam path, particularly atmospheric turbulence, represented here, when observing distant objects. And these turbulences degrade the beam in the two directions. It blurs the laser spot and the image return on the sensor. This is what is illustrated on the left of the slide, where you can see that the point is no more a point, but a blurred spot and fluctuating over time. The classical solution to overcome these disturbances is to oversize the system, the design, the power emitted from the laser, and therefore the cost to achieve the required performances. And for example, we can imagine to implement a higher power laser than strictly necessary. From an engineering point of view, oversizing means more complex design with impact on size and robustness, and it can be a nightmare to imagine relevant solutions. And from the user point of view, complexification means a more expensive system. So I bring back to the main pillars, the main topics of interest when designing a solution. So high-power deformable mirrors are a technology to manage the perturbation caused by turbulences. This technology allows us to measure the turbulence in real time via a wavefront sensor represented here, and compensate these turbulences in the past via a deformable mirror, which is in a closed loop with the wavefront sensor. So we measure in real time the distortion of the wavefront in the wave path, and we introduce thanks to the deformable mirror, the, let's say, opposite of the distortion in the wave path, also in real time, to get back to the ideal case. This results in a planar wavefront at the sensor input, bringing us closer to the ideal case. And to get an idea of the contribution of this technology, we can say that we address around 80 to 90% of the disturbances. This is what you can see on this slide. On the left, you can see the image of a spot without correction. And on the right, you can see the image with correction in real time. So even if it's not perfect, it highly improves the quality of the image. So this technology is available, mature, widely used, and is easily integrable given the compactness of the basic components, with very positive effects on our systems. And as I said before, it opens new perspectives. So for our optronic system, and especially the optronic site I presented earlier, high-power deformable mirrors are a breakthrough, offering new benefits on the left of the slide, and applications to our customers on the right of the slide. I mentioned the invariance of harsh environments, fine stabilization, and cost. Introducing adaptive optics technology into our system allows, all things being equal, especially the optronics performances, simpler optomechanical design, making them more robust in severe environment. Simpler designs also mean lower acquisition and ownership cost for our user. On the right now, adaptive optics also enable new functions, new applications, such as optical communication and laser weapon application. These two applications involve laser imaging with the need to control a high-power laser beam and focused energy along the path, a concept known as fluence. And adaptive optics allow us to focus laser energy on the object of interest, a receiver or a threat, by controlling this laser fluence. For optical communication application, adaptive optics improve the link balance, therefore increase the bandwidth available. And for laser weapon application, it concentrates energy on the target for a quicker neutralization and threat processing capabilities. And for both, the need of managing high-power laser as the object of interest is quite far from the source. And in terms of high power, we mean something larger than kilowatts, and sometimes up to hundreds of kilowatts. No, that's okay.
Yeah.
You hear me? You hear me? Yeah.
Yes. Yes.
Okay, we now focus on these two new applications. So the first one is optical communication. So this application aims at communicate at long distance. We are talking about hundreds of kilometers, with high data rates without interference between the emitter and the receiver. And with secure links, the communication is point-to-point and highly targeted at the receiver. Therefore, no risk to spread the information and be listened by an unwelcome third party. The second application is direct energy weapons, also known as DEW, to neutralize threats, especially emerging drone swarms that cannot be effectively countered by conventional munition. So it is really a new emerging threat to be considered. And laser weapons have no ammunition constraint, a low cost per shot, and the ability to scale neutralization by modulating power. So it's really a breakthrough to deal with this new new threat. For this application, it is necessary to have systems that can compensate in real-time turbulences due to the relative speed between the emitter and receiver, which induces rapid turbulence changes. And the notion of relative speed is a very important notion. So we have a first negative contribution from turbulences, the classic one, I would say, along the optical path. But we have a second negative contribution, the fact that the transmitter changes its sight axis over time from right to left in the pictures shown on the slide to follow the object of interest. And sometimes he has to do it very fast, especially for this kind of application. And this movement introduces another variation of this turbulence along the scanned area. And this variation comes with a lower time constant in the phenomena. Turbulence, therefore, evolves along two dimensions, time, along the beam path, and in space, through the scanned area. This system must also handle very high optical powers, kilowatt to several hundred of kilowatts. And these capabilities combined together lead to high fluence, meaning the ability to deposit a large amount of energy on a small surface. And it's like using a magnifying glass to concentrate sunlight on a specific area, which can quickly ignite. So as a conclusion, high power deformable mirrors are keys to address these new applications as it allows us to first significantly attenuate turbulence effects. Remember the 80 to 90% improvement mentioned earlier. While we don't achieve a perfect point, we get something much more focused. We have to do it very quickly. Turbulence evolves over time along the beam path and in space during the scanning, relative wind speed due to the relative movement of the emitter and receiver. And this requires very high frequency modules. This is also a challenge. 500 Hertz to 1 kilohertz for static links with no scanning, therefore only natural atmospheric wind, and up to 4 to 5 kilohertz if there is a relative movement leading to the accumulation of the two types of disturbances mentioned earlier. And the third topic is the need to use deformable mirror that can withstand the emitted power, which is a challenge. We send several kilowatts to reach the object of interest, and the deformable mirror must reflect while compensating for the emitted power without deterioration. And this is the end of my talk. I hope that it was clear, interesting, and thank you very much.
Thank you very, very, very much, William. And actually, it catch a lot of attention. There are a lot of questions coming out. I remind to all the attendees to come to the Q&A box to continue doing your questions. We will address all of them at the end of all the presentations. So thank you very much. That was really nice to know, like all the applications that you can do with the mirrors is really important. It's not only defense, but it's also medical, and there are so many other applications to have to keep an eye on it. Now, our second speaker today is Dr. Jonas Ohland. He's a distinguished researcher in the plasma physics at PHELIX, Germany, at GSI. Jonas is currently a postdoctoral researcher, as I say, GSI Helmont Center for Heavy Ion Research, and he will focus in advancing high-power laser systems and their applications in cutting-edge research, including nuclear fusion. So Jonas has contributed extensively to the understanding of laser-matter interactions. His work spans fundamental research and practical innovations, addressing challenges in high-energy laser systems with solutions that have both scientific and industrial significance. So Jonas will take us through the fascinating role of adaptive optics in laser fusion. Jonas, the floor and the attention is yours.
Great, thank you very much. So it's a great honor to have the chance to talk a little bit about the work that I've been doing in the last couple of years, which was, as already mentioned, wait a second, laser pointers here, all right. Adaptive optics in high energy laser systems. And today I'm going to introduce you to a very specific application of this technology, which is inertial fusion energy. So I'm taking some time to introduce you to this topic, and then we switch over to adaptive optics, where we currently are, what we need, and what the future plans are for that. So I think it's not quite necessary to talk about in detail why fusion energy is a good idea. So nevertheless, here is a plot where we've got the global energy consumption on the y-axis and time on the x-axis. And the different colors here, they are basically associated to different sources of energy. And here on the top, we can see that even though renewable energy sources are on the rise, the global demand of energy still increases much faster, which means that we are still burning more and more fossil fuels every year. So, I mean, even though fusion energy is probably not right around the corner, once we solve it, we can basically replace this bulk energy demand down here with clean, abundant, and safe energy. So there are different ways on how to achieve fusion energy. One of them was already mentioned by Vivien, which is magnetic confinement fusion as done at the ARTAO facility. So this basically you have these donut-shaped chambers with strong magnetic fields that confine the plasma. It's then heated with microwaves up to the point where we get fusion. So that is one very well-known way to do that, but there are plenty other ways which are currently being investigated. And one technology in particular gained some significant attention over the last years, which is inertial confinement fusion, or ICF. So this approach works very different, and the first difference that strikes the eye is that the fusion is actually the fuel for the fusion is actually contained in this tiny spherical pellet here instead of a large chamber. And the way that we are approaching this is that we take this pellet and we shoot onto the surface of this pellet from all directions with highly energetic laser pulses, which then ablate the outer shells of this capsule here. And the ablation pressure then drives inwards all the fusion fuel to one certain point, the center point, if we do it well. So we need a very homogeneous compression in order to achieve that. So then when we reach sufficient density, which may be in the order of several times the solid state density and temperature, then we can ignite fusion in the central hotspot, which will then basically launch a fusion burn wave, which burns from the center to the outer parts of the shell. And this reaction is then just confined by the inertia of the outer parts of the shell. So that's why we call it inertial confinement fusion. So conceptually, this is relatively simple, but of course, it's a whole different story if you actually try to achieve this. And the most elaborate experiment that we currently have on this planet is the National Ignition Facility in the United States. So this is a quite huge facility. So this laser hall here takes up the space of about 3 American football fields. So here you can see a photograph of one of the 2 laser halls. And the whole facility hosts about 192 high-energy laser beam lines, which shoot simultaneously in order to make this little fuel capsule collapse and start the fusion reaction. So a couple of years ago, in 2021, there was a big breakthrough where the National Ignition Facility, first of all time, achieved this fusion ignition. Since then, they tweaked a couple of parameters, and right now they achieved a gain of about 2.4. That is basically the comparison of the energy that goes out of the fusion reaction compared to the laser energy that goes in. So this is already a great progress. However, if you want to use that commercially at some point, we need to get up to a gain of approximately 100. There are different ways on how to get there, so scale things up, use different drive schemes and so on. But this is not the only bottleneck that needs to be overcome in order to make this commercially feasible. The other thing that is really limiting is the shot rate or the repetition rate on how often per unit of time we can do this fusion reaction here. So for commercial power plant, we would need to do this about 10 times per second. However, today, the National Ignition Facility can only do that 3 times per day. So that is obviously a huge, huge difference. And we need to do a lot of things in order to get around this limitation. And this is basically the area which we are talking about today. So before we get to the topic of adaptive optics, I think it absolutely makes sense to understand where this shot rate limit of 3 shots per day actually comes from. And for that, it's very useful to talk about how these laser beam lines here actually work. So say you are now a laser engineer, you have the task to generate lasers for fusion, then you have one big goal. That is maximize the energy per laser pulse that the system can deliver, but only so much that you don't destroy the laser with this very same laser pulse. So you have to find a smart way to get around this limitation of optical damage thresholds. And the way that is usually being done is to employ an architectural concept which is called MOPA, or Master Oscillator Power Amplifier. And it kind of works like it follows. So we start the laser chain with what we call the master oscillator. So this can be any laser source. It can be like a textbook resonator with an active medium in the center, or a fiber laser, so that there are different ways to do how to do that. From the Gaussian laser beam that exits this laser, we cut out a tiny piece from the center in order to get a more like a top hat flat laser beam profile, because that's just way more efficient to extract power from our laser amplifiers. After that, we implement a telescope, which kind of widens up the beam, because a wider beam means lower fluence, and thus it's less likely that you burn your optics. And once you've done that, you can slam in the first amplifier of the system. So the amplifier is basically just a bulk material with an energy pump, so in more or less the same way as you use it in the oscillator. Just this time, we don't use a laser resonator, but we just pass the laser pulse through the material, and therefore it gains energy by doing so. So by doing this step, by first magnifying the beam and then amplifying, we can actually do 2 more things which are quite important for this architecture. And the first one is spatial filtering, where we basically pick the focal point of the laser here and remove all these scattered rays of light here. That removes the high spatial frequencies. It basically cleans up the beam, so we don't get hotspots in our amplifiers or in the mirrors or something, so we don't burn things. And the second thing that is very nice is that, I mean, we already have an imaging system with this telescope, so we can basically transport the image of the aperture into our laser amplifier or any other point of significance. And that has the huge advantage that we kind of limit the diffraction of the laser beam here, again, keeping a very homogeneous laser beam profile and not burning anything. And that basically is already the cookbook recipe for high energy laser systems. You can then repeat the steps, so widen up the beam, slam in another amplifier, do relay imaging, and probably another time up to the point where the beam diameter is so large that it just becomes unfeasible to generate larger optics. And then you can hand over the laser beam to your application. For example, just focus it down onto some point of interest, what we call the target. That could be a fusion pellet or something else. So now you have a basic understanding on how these laser systems are structured. So now we can discuss why we have this shot rate limit. And the secret lies in these amplifiers here. So you see that the last amplifier that I sketched out here looks a little bit funky compared to the other ones. That is meant to resemble what we call a slab amplifier. So this is a photograph of a laser amplifier module that we use at the PHELIX laser. So the National Ignition Facility uses very similar ones. Basically, we have these neodymium-doped glass slabs, which are oriented in the Brewster angle in the laser beam, so we don't get a lot of losses from reflection. And these are then pumped by flash lamps, which are located left and right of these laser amplification discs. So neodymium glass is a great choice when you want to deliver highly energetic laser pulses, because the neodymium ions in the glass can store a lot of energy, which is useful, obviously. However, it is at the same time a very bad choice because glass is horrible at transporting heat. So you all have these little quantum defects. So the energy that you pump into the glass does not get converted 100% into laser energy, but also to some part in heat. And we all know that things that get warm tend to deform. If optics deform, our beam deforms, and there we are, we've got aberrations that we kind of have to get rid of. And this is really the thing that limits the shot rate of the National Ignition Facility, because they have to wait several hours until most of the heat got out of the system, so they can do this repeatable experiments where they have to compress this capsule in a very precise manner. So there are a lot of people investigating on how we could do better here. So one option would be to use a different material that is better at heat conducting, or use some more elaborate cooling schemes and so on. But also, obviously, one way to do that is to use adaptive optics in order to counteract these aberrations that you get from the heat source here. So yeah, adaptive optics in these very highly energetic lasers is kind of a different beast compared to other applications, because we have very specific challenges that are specific to this environment here, and these have not been fully addressed yet. So the first challenge that we have with adaptive optics in high power lasers are the large fluences and the large apertures. So the lasers that we are using produce a significantly higher power than the ones that are used in defense applications, for example. That's why these things take up entire football field sized halls. That basically means that you can't use these very nice MEMS mirrors that are, for example, produced by Boston Micro Machines or Alpao. Even though they are very nice devices, these very delicate membranes, they would just burn up in the power that we deliver here. And furthermore, because we have these large laser beams, so the laser beam at PHELIX, for example, has a diameter of about 30 centimeters, it just makes the production of these mirrors basically impossible. So the two deformable mirror technologies that we are using are, on the one hand, just plain piezoelectric bimorph mirrors, where you have this glass membrane with some piezoelectric ceramic on the backside. These scale quite well to centimeter diameters, and you can apply high power coatings to them so they don't burn up in our laser pulses. And we basically use them for pre-compensation relatively early in the system. The other technology that we use are mechanical deformable mirrors. So this is a photograph of the mechanical deformable mirror that we use at the PHELIX laser. It can accommodate a beam size of about 30 centimeters. And the way they work is that we just have these stepper motor driven actuators which apply force to the glass membrane of the mirror and therefore generate these deformations. This is great because we can do semi-static compensation of aberrations. So once the mirror has assumed a shape, we can basically pull the power plug and it will remain there indefinitely. The downside is, of course, that these actuators are relatively slow. It's stepper motors in the end, so this is only for semi-static compensation and not for real-time compensation of adaptive of aberrations. The second large challenge is the limited shot rate. So that may sound a little bit counterintuitive because we want to use adaptive optics to increase the shot rate. However, right now we don't have an awful lot amounts of shots. So imagine you have a laser system which is actually already capable of shooting 1 time per minute. This is still far from enough to feed a feedback loop with data that is sufficient to counteract air turbulence, for example. So these are really the two challenges that kind of hinder us in our field, and therefore we need ways to circumvent them. And that's exactly the topic which I'm currently working on. And this is funded by the European THRILL program. So that stands for Technology for High Repetition Rate Intense Laser Laboratories. And this is a research program which is entirely dedicated just to advance the technology that is incorporated in designing, building, and running these highly energetic laser systems, which are then also relevant for inertial confinement fusion. So let's get to the actual application here. The first laser where we try to implement that is actually not for fusion. It is the Appolon laser in France, which is a titanium sapphire laser system. It has a slightly different objective. So instead of delivering high energies in the output, it tries to deliver these high peak powers. So about 10 petawatts is the peak power that this laser can achieve, which is very, very crazy. But still, this MOPA concept that I described earlier does apply. So down here, you have a drawing of the amplification area of Appolon. So this is a full laboratory-sized hall here. And we deliver the master oscillator pulse into the room from up here. Then we have this huge optical table, which contains the first 3 amplification stages of Appolon. And here we are using these multi-pass titanium sapphire amplifiers. These are these bow-tie-shaped structures here, where we run the laser beam several times through the same titanium sapphire crystal to extract energy. And you can see there are 3 of them in different sizes. That is exactly this Nolper concept, where we expand the beam over and over again in order to increase the energy. And after the end of it, we have about 30 joules in our laser pulse. And then we enter the last amplifier, which is this one, of course. It's also a multi-pass amplifier, and it uses one of the world's largest titanium sapphire crystals by this date, and has a beam diameter of about 14 centimeters here. This structure is relatively large, so we have a size of 12 meters just for this amplifier alone. And having a beam that large running through laboratory air over that distance means we are susceptible to density fluctuations in the air. And prior to this work, when we did some measurements on the wavefront fluctuations, so here's a real-time playback of that, we see that if we look at the focal spot that is generated by these aberrations, that this is moving at a rapid pace. So relatively speaking, it's of course much worse when you deal with exterior atmospheric turbulence, but still you can't really do reliable plasma physics experiments, yet alone fusion with a laser focal spot that moves in this manner here. So the first thing that we did is, of course, to build a better beam housing. That helped a lot, so just keep out some of these turbulence. But at the same time, we realized that this is not going to cut it. We need some active stabilization routines to actually get to the specs that Appolon is supposed to deliver. So how did we do this? Here's a more simplified sketch of the beamline of Appolon. So we have our main pulse source here. We run it over a small biomorph deformable mirror. Then we have these 2 amplifiers here with air turbulences in between. And right before the beam enters into the vacuum chambers of Appolon, we just grab a little bit of the beam through a leaky mirror and feed our wavefront sensor with that. Of course, by now we all know that our main source is pulsed, and we will not be able to run a real-time loop on the main source. So we kind of drew some inspiration from astronomy and built our own little artificial laser guide star, which is basically a continuous wave laser beam where the wavelength is detuned with respect to the main spectrum of the Appolon laser system. So we can use a dichroic mirror to inject it into the beamline. It then co-propagates with the main beam, picking up all the aberrations that are in the system. And then we separate it with another dichroic mirror. And now we are able to have a real-time feedback because we have data all the way through. So the way we implemented this loop is to use a high-speed PCIe camera from Ximea, which is able to deliver about 7,000 frames per second into our computer. We equipped it with a microlens array, and so in order to form a Shack-Hartmann sensor, and then that gets handed over to the graphics card of our real-time computer. So this real-time computer is running actually an open source adaptive optics software. It's called Cacao. So Cacao was developed for astronomy, specifically by the SCAXAO team of the Subaru Observatory on Hawaii. And they have been incredibly helpful to help us setting this software up on our computer, how to operate it and how to extend it with the capabilities that we need. So thank you very much to the team for that. And once we have our control signal that Cacao spits out, we can then connect our deformable mirror here in the beginning. And so this is a biomorph deformable mirror with about 6 centimeters of aperture, and we update it about 1,300 times per second. So let's look on how this system performs. So here on the left side, we've got a plot where on the x-axis there's time. On the y-axis, we've got the Strehler ratio, at least like a relative Strehler ratio, so where we compare the beam with a reference wavefront. And we can see that without adaptive optics here on the left, that there's a lot of fluctuations. But once we turn on the loop, we get a much better beam stability over here. I think it's even easier to see in the histogram view of this data. So the red curve here represents the time series without adaptive optics. On the x-axis, that's the Strehler ratio. On the y-axis, that's the counts. And the blue axis is then with adaptive optics. And we can see that we get a beam quality which is consistently above 0.96 in terms of the Strehler ratio. So that all sounds very good. However, we are not done yet because we still have a serious issue that we need to tackle. So again, here in this plot, we've got a time series, but this time it's over almost 2 hours. On the y-axis, we've got the RMS of the wavefront. So the higher the data point, the worse the beam actually looks. And we see that even though things look very stable for the first 30 minutes, after that we get these single breakout wavefronts which feature a much worse quality. And after the 1 hour mark, things get completely crazy and we get these extended streaks of instability here where the beam quality gets very bad. And this is needlessly to say something that we can't use for our experiments. Luckily, we know where this is coming from. This is due to the sorry, that's a very complicated word, misregistration error. That basically means because our wavefront sensor is so far away from the deformable mirror that if the temperature changes ever so slightly, we may experience a shift of the image of the deformable mirror on the wavefront sensor. So the actuator positions in the actual image do not correspond to the reference actuator positions anymore, and the loop becomes unstable. So this is particularly a problem for our laser systems because the strokes in this unstable state become so large that the deformable mirror is able to inject these hotspots into the wavefront that you see here. And that is basically a death sentence for this application because that would immediately burn all our optics once we deliver a full energy shot. So we really, really need to resolve this problem before we actually use it to deliver shots here. So yeah, in this case, it will boil down to having a proper tracking system. So I see I'm already quite far in the time, so let's wrap it up here. I talked about the Appolon Real-Time Adaptive Optics, or ARTAO, project that we ran in France. So this is an astronomy-inspired real-time AO system, which solved the single-shot issue with a pilot beam approach, and we were able to achieve a significantly better beam stability with the system. There's still to-dos though, so we need to find a way on how to properly compensate for these beam drifts here, and we need to bake machine safety into our adaptive optics loop to make sure that it never, never, ever fails before we deliver the shot. That would be a very expensive mistake otherwise. So lastly, to go full circle, let's return to fusion energy. That's where we started. So obviously we need a very good beam quality for fusion, but we also need higher repetition rates. And by using an adaptive optics system like the ones that we demonstrated at the Appolon laser system, we will be able to significantly increase this shot rate on its own. And if we combine that with other measures for increased shot rates, that will be a significant part towards progress, towards success with fusion energy. And with that, I would like to thank you very, very much for your attention.
Thank you so much, Jonas. This is actually, I mean, a great presentation, and you are addressing the main issues that they are with fusion energy. So the fluids, the repetition rate that is needed is we are very far to keep the 10 Hz. In your opinion, what could be done to achieve that?
Come again? I don't think I understood the question.
Okay, so we are one of the things that is already very well known is repetition rate that is needed is in the 10 Hz. Okay, so yeah. So what do you think it is done? It can be done to achieve that beyond what your work? Yeah.
Yeah. So this is a very very multidisciplinary question. Actually, I know that people are continuously working on different laser materials, for example. So they want to switch to cryogenic crystalline materials, which are obviously much better at conducting heat outwards. I also know that there is a significant effort in increasing the pump efficiency. So all the energy that goes into material is converted more efficiently into laser energy and less efficiently into heat. So these are things that are currently being investigated. But of course, once we get to 10 Hertz, there will still be some residual heat that we need to counteract. And therefore, adaptive optics will be one part of the puzzle.
Yes, absolutely. I totally agree with that. Okay, so let's go with the questions. We have so many questions. This is like a high record here. It's such an interesting subject. So there is a question here to Vivien. So what is considered in high power? How many watts are we talking about? Can you comment on pitch area and the whole mirror and size and single mirror LED, and how these quantities are according to the applications they are used in.
Okay. What I can say regarding the power, so we are talking about kilowatts up to 100 of kilowatts. For example, for the Jew application, you hear me? Yes, it's yeah.
Yeah, yeah, yeah.
Yeah, for the Jew application, we need to send kilowatts to make sure to take care of the threads, and also for communication as the satellite are very high. I haven't caught the other questions.
Yeah, so that was Philip that was saying, can you comment on pitch, area of the whole mirror and size of a single mirror LED, and how these quantities vary according to the applications they are in using?
Okay, I am not going to answer right now. I take the point. I take the question. I got back. I have to talk with the engineer guy to bring back with a relevant answer.
Yeah. So let's go down. So for Jonas, is the deformable mirror relay imaging with amplifier gain media?
So that is, of course, a design consideration that you have to meet specifically to your system. So at Appolon, we had the issue that this was kind of a retrofit for the system. So the system was already in place, and we had very limited space where we could fit the deformable mirror and the wavefront sensor. So even though we would have loved to put it in the relay image plane of the amplifier crystals, which would be like a very important thing to do, we were not able to do that in this case. But of course, if you are designing like a fusion laser beamline from the ground up, you want to do exactly that. So make sure that your deformable mirror lines up with the relay image planes as good as possible. So as long as the wavefront is flat, you can be sure that the beam quality will also be nice on the crystals and all these important optics.
Yeah, there is another question here is, can the fast deformable mirror be as small as 20 millimeters diameter? And what about the electromagnetic perturbations? Are they affecting the fast deformable mirror?
Okay, that's very interesting questions. So the first thing about the deformable mirror size. So we actually considered using a smaller deformable mirror even earlier in the system. The issue that you can have there is that this tiny mirror is basically pre-compensating all the aberrations that occur in the system later on. And having that means that we actually have a lot of aberrations before the beam reaches the points where it kind of gets neglected again. And with small beams, you tend to get a lot of diffraction. So this issue that you get hotspots in the beam at critical locations early in the system then suddenly becomes very large. And this is why we actually want to do it as late as possible to keep this effect at a minimum and rather compensate at a larger beam. So concerning the electromagnetic influences that we face there, that is a very valid question. I mean, if we do experiments and we shoot with the laser onto some sort of target, we usually get extreme electromagnetic pulses there, which could potentially interfere with the adaptive optics system. But there, I have to say that it's rather dangerous to have your computer shut down because of the EMP than that the mirror actually moves at this time scale, because I mean we're talking about things that unfold with the speed of light here, and mechanical movements will never be that fast. And yeah, so but usually we do the control sufficiently far away from the target chamber, so this is not really an issue.
Yeah, excellent. So there is another question says, I suppose the wavefront sensor requires a sharp reference point on the target. How do you obtain that, considering you need functional AO to get a sharp laser spot in the first place?
So I think we are starting to mix up two different problems here. So at least for now, we tend to think about optimization of the focus spot separate from the stabilization of the beam. So I showed this semi-static mechanical deformable mirror before. So these mirrors are usually very, very close to the interaction chamber. So it's really the last stage correction of the laser spot. And that will happen inside a vacuum chamber. And if we do that inside the vacuum chamber, there will be no more turbulence. So if we do the stabilization before, we can kind of decouple these two things. So keep the beam stable and then run the optimization with the semi-static mirror. So that's the way we approach it right now.
Okay, okay. As we see an interest in lower wavelength high power systems, the residual mechanical flatness of the DM becomes a huge issue. Is Alpao working on improving this print thought error on the actuators? Is there any job on that, William?
No, maybe because I am not a Alpao guy, so I'm not mastering the parts. But maybe I can let Valentin answer the question if he is still here.
Yeah, Valentin is here. Valentin, can you please answer this question? Valentin, we cannot hear you. Okay, well, while you are answering this, please answer on the box meanwhile, and we continue. So yeah, it was going to follow that question. So does the system comprise active cooling possibilities?
Can you hear me now?
Oh, now I can hear you. Yeah. Please, Valentine. Yeah, go ahead.
Sorry, I lost my voice today, so it's a bit hard for me to answer, but I'll do what I can. So yeah, David, we would like to be working on that subject. I believe we've been in contact before, so I'm guessing we are open to work on that specific subject, and we'll try to make something that works for you as well on this specific matter.
Okay, thank you so much. Okay, so another questions that we having is respects to this. So is the speed of the DM response to stabilize turbulence in flight applications, and how much wavefront corrections are typically needed. So how many PI or wavelength correction in your presentation, William?
Yeah, where did the question in the discussion in the chat?
So what is the speed of the DM response on to stabilize turbulence in flight applications, and how much wavefront corrections are typically needed?
Maybe I have talked about during my presentation of the response time of the deformable mirror, which is depending on the application, it has to be up to 5 kilohertz, which is a challenge. In fact, I'm not sure I am answering the question. Yeah. Can you address the following question? Speed of DM response to stability turbulence in flight applications. So up to 5 kilohertz. And how much wavefront correction are typically needed? I'm not sure I understand the question. In fact, how much wavefront correction?
Maybe I can take this one as well,
yeah.
William. Okay, so yeah, to make things fast, the faster the better in order to correct anything on sky. If the turbulences are active and they are dynamic, then both speed of the DM and speed of the actual AO loop are very important, but also latency is something that is critical. The amount of correction you need is really dependent on the sky that you're observing through. So if you're, for example, in a CT setup, you probably will need to have quite a bit of stroke on the DM to be able to correct for the whole turbulence. If you're in a very clear sky, just like the astronomers do, for example, in that kind of setup, it's much more favorable. So you need less stroke. But let's say a few wavelengths at least is a good number. Let's say, for example, 2 wavelengths is the bare minimum to be able to correct all the turbulence that is going on.
Okay, so we have another question here. So, dear Jonas, thank you for your talk. As I understand, to focus correctly on a target in the air, for example, a drone, you will need to know how atmospheres affects the wavefront, but we don't have a wavefront sensor on the drone. So the question is how exactly to see the implementation of DM for defense against drones. So we have to go through all possible parameters on DM to get necessary power density on the target in the air. I think this is for both of you.
Yeah, I think I would keep that one for Bertin Alpao.
For Bertin, yeah.
In fact, we measure the input and the output, and we correct the we do the correction in the both input output perturbations. In fact, maybe I am not clear. Sorry.
Okay, so we can continue with this. So okay, so there is a very short question here. You see, power is continuous wave or pulsed? 1,000 kilowatts.
Yeah, it depends on the way you want to address the threat. Continuous lasers are often preferred for sustained damage if you want to, in fact, destroy the drone. While pulsed laser may be used for precision strike on sensors or electronics. So if you want to destroy the threat, you use continuous laser. If you want to destroy the electronics and therefore the ability of the drone to fly, we use pulse laser. For the time being, the systems are mostly based on continuous lasers.
Okay, so there are so many interesting questions, but we start in time, we finish on time, and this is the moment. So we can all, you can all reach us at Optica or at Alpao. So this will conclude our industry tutorial on high-power deformable mirrors for laser and defense applications. Huge thanks to our speakers, Vivien, and Jonas Ohland for sharing their experience, and to Bertin Alpao for their support. And thank you, to all of you, our audience, who engage and so provoking questions. You want to be introduced to Bertin Group, Alpao, or any of our corporate members, please contact us at industry@optica.org or myself directly, hts@optica.org or jpook@optica.org. Thank you so much. See you next time.
Thank you. Goodbye.